Most people believe the first sign of danger from Etna will be a pillar of ash in the sky. The terrifying truth is, the first sign will be the ocean disappearing from the horizon. The new rhythmic tremors spiking under Etna are not a precursor to a lava flow. They are the sound of the volcano's unstable flank, losing its final point of friction with the bedrock below. Geologists now understand this sound is not a warning of what is coming out of the crater, but of what is about to slide into the sea. What makes this tremor the point of no return for the flank collapse? And how could a silent slip on a volcano in Italy send a devastating wall of water to the coasts of Africa and Greece? Mount Etna stands as Europe's most active volcano, a colossal fire-breathing giant that has shaped Sicily's landscape and culture for over 500,000 years. Rising 3,329 meters above the Mediterranean Sea, this stratovolcano is not just remarkable for its height or activity, but for its unique geological position. Unlike most volcanoes that form along predictable tectonic boundaries, Etna exists at a complex intersection where the African tectonic plate subducts beneath the Eurasian plate. This creates a geological anomaly, a volcano sitting atop a tectonic collision zone while simultaneously being pulled apart by extensional forces. The result is a volcanic system unlike any other on Earth. Archaeological evidence shows human settlements have existed in Etna's shadow for at least 8,000 years. The fertile volcanic soil has long supported thriving agriculture, creating a dangerous paradox because the same force that threatens destruction also provides unprecedented fertility. Ancient Greeks recognized this duality, and they created the myth of Typhon, a monstrous giant trapped beneath the mountain by Zeus, whose fiery breath creates the eruptions. But Etna's true scientific story is even more fascinating. It began forming underwater around 600,000 years ago, only emerging above sea level approximately 300,000 years ago. This makes Etna relatively young in geological terms, explaining its extraordinary activity. What most people do not realize is that the Etna we see today is actually the fifth volcanic system to occupy this position. The previous four collapsed catastrophically, leaving behind remnant structures like the Valle del Bove, a massive horseshoe-shaped depression on Etna's eastern flank. This history of collapse is crucial to understanding today's threat. Geologists have identified layers of volcanic debris extending over 30 kilometers into the Ionian Sea, clear evidence of ancient flank collapses that generated tsunamis. Recent seafloor mapping has revealed underwater debris fields that can only be explained by massive volcanic landslides. What makes Etna particularly dangerous is its internal structure. Unlike many volcanoes that have a solid, stable core, Etna is built primarily from layers of ash, fragmented lava, and pyroclastic deposits, essentially a massive pile of loosely consolidated volcanic material. Over time, magma rising through this structure creates a network of weaknesses that fractures the mountain from within. The volcano sits atop a mobile substrate of soft sedimentary rocks, which deform under the immense weight above. This creates a fundamental instability. Etna is essentially balanced on a foundation that is slowly giving way. Imagine building a skyscraper on wet clay, and you begin to understand why geologists are so concerned about its eastern flank. Most critically, Etna's eastern side faces directly into the Mediterranean Sea without any natural barriers. When volcanic flanks collapse on land, they create devastating debris flows. When they collapse into water, they create something far worse, tsunamis, that can propagate across entire ocean basins. Historical records document at least 69 major eruptions in the past 2,700 years. The most catastrophic occurred in 1669, when lava flows destroyed part of Catania, killing an estimated 20,000 people. What is often overlooked is that this eruption coincided with significant ground deformation and seismic activity along the eastern flank, precisely the pattern we are seeing today. Recent scientific drilling projects have revealed another disturbing fact. Etna's magma reservoir is significantly larger than previously thought. Current estimates suggest a primary magma chamber containing over 500 cubic kilometers of molten rock, enough to fill Lake Erie. This massive reservoir not only fuels eruptions, but also heats and weakens the surrounding rock structure, accelerating the destabilization process. The combination of these factors, a volcano built from loose materials, sitting on a weak foundation facing an open sea, with an enormous magma reservoir beneath, creates the perfect conditions for catastrophic flank collapse. It is not a question of if, but when. To understand why current activity raises alarm bells, we must first establish what constitutes normal behaviour for Europe's most active volcano. Etna typically follows well-documented patterns that volcanologists have tracked for centuries. Under normal conditions, Etna experiences what scientists call strombolian eruptions, moderate explosions that eject lava fragments hundreds of meters into the air. These spectacular but relatively minor events occur from the four summit craters, Voragine, Bocca Nuova, Northeast Crater, and Southeast Crater. On average, Etna produces 3 to 4 significant eruptions a year, with continuous minor activity between these events. The volcano typically gives clear warning signs before major eruptions. Seismic swarms, clusters of small earthquakes precede magma movement. Ground inflation, measured by GPS stations across the mountain, indicates rising magma pressure. Gas emissions, particularly sulfur dioxide, increase dramatically as magma approaches the surface. These signals usually emerge days or weeks before an eruption, giving authorities time to implement safety measures. What makes Etna relatively safe despite its frequent eruptions is this predictability. The Italian National Institute of Geophysics and Volcanology maintains one of the world's most sophisticated volcano monitoring networks on Etna, with over 300 instruments providing real-time data. This allows scientists to forecast most eruptions with reasonable accuracy. Under normal conditions, Mount Etna's eastern flank experiences slow, steady movement toward the Ionian Sea. This phenomenon, known as flank creep, has been measured at approximately 2 to 3 centimeters per year. This movement occurs along several fault systems, with the Pernicana fault to the north and the Tremestieri fault to the south, acting as boundaries for the sliding sector. This steady creep is actually a safety valve. It releases accumulated pressure gradually rather than suddenly. As Professor Boris Benker of INGV explains, the constant movement prevents catastrophic failure by releasing strain energy before it reaches critical levels. It is when this movement pattern changes that scientists become concerned. Etna's magma also follows predictable paths. Most eruptions begin with summit activity, before potentially progressing to flank eruptions through lateral vents. These lateral eruptions typically form along two main rift zones, the Northeast Rift and the South Rift. These established pathways channel magma away from the unstable eastern flank, further contributing to the volcano's relative safety. Even Etna's more significant eruptions follow recognizable patterns. The 2001 eruption, which threatened the town of Nicolosi, began with summit activity before progressing to flank eruptions. The 2008 to 2009 eruption followed a similar progression. In both cases, authorities had adequate warning to implement evacuation plans. The volcano's lava composition also remains remarkably consistent. Etna produces basaltic lava with relatively low silica content, making it fluid and fast-moving but less explosive than other volcanic types. This consistency allows scientists to anticipate how eruptions will develop once they begin. Even Etna's effect on surrounding communities follows established patterns. Ashfalls primarily affect communities to the east and southeast, based on prevailing wind patterns. Lava flows, historically, follow predictable pathways determined by topography. This allows for effective hazard mapping and emergency planning. What makes Etna's current behaviour so concerning is precisely how it deviates from these established patterns. The rhythmic tremors now being detected do not match the seismic signature of rising magma. They do not correlate with summit activity. They do not follow the timing or progression of typical eruptive sequences. Instead, these tremors are occurring along the submarine continuation of the eastern flank, far from the volcanic conduits, where activity normally begins. They maintain a metronomic regularity, occurring at precise intervals, unlike the chaotic random pattern of typical volcanic seismicity. Most alarmingly, these tremors coincide with a dramatic acceleration in flank movement. GPS stations along the eastern slope now record movement rates of up to 5 centimeters per month, more than 20 times the normal rate. This acceleration does not follow gradual seasonal changes, but shows sudden, dramatic increases coinciding with each tremor episode. As Dr. Marco Neri of INGV notes, we are seeing a fundamental change in how the eastern flank is behaving. It is no longer releasing pressure gradually, it is accumulating strain energy in a way that suggests catastrophic failure may be imminent. The first indication that something fundamental had changed came on March 17th this year, when seismic stations across eastern Sicily began detecting an unusual signal. Unlike the chaotic, random patterns typical of volcanic activity, these tremors maintained a precise rhythm, occurring every 43 seconds with mechanical regularity. Initial analysis suggested these might be what volcanologists call long-period events, harmonic tremors caused by magma moving through narrow conduits. But something was different. These signals were not emanating from beneath the summit craters, where magma typically accumulates. Instead, they originated from deep beneath the eastern flank, in an area where no known magmatic pathways exist. More concerning was their depth, approximately 8 kilometers below sea level, far deeper than Etna's primary magma reservoir. This placed the source within the sedimentary basement on which the volcano sits. As Professor Carlo Doglioni, president of Italy's National Institute of Geophysics and Volcanology, explains, these tremors are not coming from within the volcano itself, but from the foundation it is built upon. It is like hearing creaking sounds from the supports of a building rather than activity inside. Satellite interferometry soon confirmed the worst fears. INSAR data, which can measure ground deformation with millimeter precision, revealed that an enormous section of the eastern flank, over 700 square kilometers, was moving as a single coherent block. More alarmingly, this movement was accelerating exponentially. Historical records show the eastern flank has been creeping seaward at 2 to 3 centimeters annually for decades. Current measurements show movement exceeding 7 centimeters in just the past month. This acceleration coincides perfectly with the onset of rhythmic tremors, suggesting a causal relationship. Marine sensors deployed along the submarine portion of the flank detected another disturbing phenomenon. The seafloor itself is bulging upward, clear evidence that massive pressure is building beneath. Precise, bathymetric mapping shows vertical displacement of nearly 2 meters along a 15-kilometer arc offshore, a deformation that can only be explained by catastrophic structural failure. What makes these signs particularly ominous is their remarkable similarity to precursors observed before other devastating flank collapses worldwide. Before the catastrophic 1980 collapse of Mount St. Helens, scientists recorded similar rhythmic tremors and accelerating deformation. Before the 2018 flank collapse of Indonesia's Anak Krakatau, which generated a deadly tsunami, satellite imagery captured comparable patterns of movement. The evidence suggests a terrifying scenario. Etna's eastern flank is detaching along a deep-seated fault plane. Each rhythmic tremor represents a small slip along this fault, gradually reducing the friction that holds the flank in place. As friction decreases, movement accelerates, creating a deadly feedback loop. Thermal imaging provides further evidence of imminent collapse. Infrared satellite data shows a distinct temperature anomaly along the failure zone, not hot enough to indicate magma, but significantly warmer than surrounding rock. This thermal signature suggests frictional heating along the fault plane, another classic precursor to catastrophic failure. Perhaps most concerning is the discovery of submarine gas emissions along the projected failure plane. Remotely operated vehicle surveys have identified dozens of new gas vents on the seafloor, releasing primarily carbon dioxide and hydrogen sulfide. These emissions indicate that seawater is now penetrating deep into the failure zone, weakening the remaining friction points and potentially lubricating the slide plane. Geochemical analysis of these emissions reveals another disturbing detail. They contain elevated levels of radon gas. Radon is released when rock fractures create new pathways to the surface. The steady increase in radon concentrations suggests the failure zone is expanding rapidly, creating new fracture networks with each tremor event. Historical data provides sobering context for these observations. Similar precursors have been documented before other major volcanic landslides. Before the 1888 Ritter Island collapse, which generated a 13-meter tsunami across the Bismarck Sea, observers reported unusual seismic activity and ground deformation for weeks preceding the disaster. The volume of material involved is staggering. Conservative estimates suggest at least 10 cubic kilometers of rock could detach in a single event, roughly 1,000 times the volume of material involved in the Mount St. Helens collapse. More alarming scenarios suggest up to 25 cubic kilometers might fail catastrophically, enough to cover all of Manhattan in debris over 3 kilometers deep. The underwater trajectory of this enormous mass compounds the danger. Computer models indicate the collapsing flank would accelerate to over 200 kilometers per hour as it slides down the steep submarine slope. The initial impact would displace an estimated 300 cubic kilometers of seawater in less than 5 minutes, creating conditions perfect for tsunami generation. Dr. Stefano Branca, director of the Etna Observatory, summarizes the situation with chilling clarity. We are witnessing the final stages of a process that began thousands of years ago. The eastern flank has always been unstable, but what we are seeing now suggests the system has reached a critical tipping point. The only question remaining is whether the collapse will occur as a single catastrophic event or as a series of large failures. The implications extend far beyond Sicily. Hydrodynamic models indicate a flank collapse of this magnitude would generate a tsunami with initial wave heights exceeding 40 meters along the eastern Sicilian coast. Cities like Catania, with 300,000 residents, would have less than 15 minutes warning before being devastated. The tsunami would propagate across the Mediterranean, reaching the coasts of Greece within 2 hours, North Africa within 3 hours, and potentially parts of Spain and France within 5 hours. The most insidious aspect of this threat is its deceptive nature. Unlike eruptions, which announce themselves with spectacular displays visible for kilometers, flank collapse can occur with minimal surface warning. The first indication for coastal communities would not be a rumble or an explosion. It would be the ocean suddenly receding from the shore as the initial wave trough arrives, followed minutes later by a devastating wall of water. This is why the rhythmic tremors now emanating from beneath Mount Etna represent such a critical warning. They are not just unusual seismic signals, they are the sound of geological forces reaching their breaking point. Each tremor marks another incremental failure in the system, keeping the eastern flank attached to the mountain, and each failure makes the next one more likely, creating a cascade effect that could culminate in one of the Mediterranean's worst natural disasters. As the tremors continue with metronomic precision, the clock ticks down toward an outcome that seems increasingly inevitable. The only questions remaining are when the final collapse will occur and whether monitoring systems will provide enough warning to save lives. The evidence is clear and increasingly urgent. Mount Etna's eastern flank is showing all the classic signs of impending catastrophic failure. The rhythmic tremors that began earlier this year are not just unusual, they represent the sound of a geological time bomb counting down to detonation. What makes this situation particularly dangerous is how it differs from traditional volcanic threats. Most volcanic disasters, such as pyroclastic flows, lava inundation, and ashfalls, affect relatively limited areas directly surrounding the volcano. A flank collapse generated tsunami could devastate coastlines hundreds of kilometers away, affecting millions who have never considered themselves at risk from Etna. The time to prepare is now. Mediterranean nations must accelerate the development of tsunami warning systems specifically calibrated to detect and respond to volcano-generated waves, which behave differently from earthquake-generated tsunamis. Coastal communities need clear evacuation routes, education programs, and regular drills. Most importantly, we must heed the warnings Etna is clearly providing. The rhythmic tremors are not just interesting scientific data, they are a final alert from a mountain that has coexisted with human civilization for millennia, now signaling that a catastrophic change is imminent. As for Etna itself, this collapse would not be an ending, but a transformation. Throughout its 500,000-year history, the volcano has experienced multiple major flank failures, each time rebuilding itself through continued eruptions. Life would eventually return to the devastated areas, drawn by the same fertile volcanic soil that has attracted settlements for thousands of years. But for now, the warning signs demand our full attention. The next time you see images of Etna's spectacular eruptions, remember that the real danger is not what is coming out of the volcano, it is what might suddenly slip into the sea. This is Earth Attacks signing off. If you found this information valuable, hit subscribe and share this video with people who need to hear it. Remember, knowledge does not just satisfy curiosity, it saves lives. Join us next week as we explore another of Earth's hidden dangers hiding in plain sight. Stay safe, stay informed, and we will see you next time.